some important things I'd like you to highlight from here. So first thing we're going to highlight is we say that the degree of a polynomial function is the highest power. So we have dealt with linear when you just have an x to the 1. Quadratic when you have an x squared. Cubic is when you have an x cubed. But now we're going to add x to the 4 graphs, quartic graphs, x to the 5 graphs, quintic graphs, and so on. Okay? The number in front of that highest power is called the leading coefficient. And the leading coefficient is going to tell us a lot about the graph and give us some hints. Like we saw in these previous ones, we noticed that with the x to the 4, when it was negative, it opened down just like a parabola, and when it was positive, it opened up just like a parabola. And we're going to categorize our polynomials by either an even degree or an odd degree. And I'm going to get you to write a couple of notes off to the side on this. And another thing that is important for next year for calculus, also important for graphing this year, the graph of a polynomial function is smooth and continuous. And they use these words lots in calculus, which means it has no sharp corners, and it can be drawn without lifting your pencil from the paper. So these graphs here have no sharp corners, right? Even though this top is pretty steep, it's still rounded at the top, okay? So there's going to be times where you might find this point, and be like, I want to draw this. You're going to lose marks if you draw it with sharp corners. You have to make sure that the graph is going rounded around those as you draw. So that's what's meant by smooth and continuous. So our notes off to the side, we're going to write some hints about even functions. So what is an even? Well, what is an even function? That's like an x squared graph, x to the 4 graph, x to the 6 graph. If your highest degree is even, you have an even function. And there's a pattern with even functions that the end behavior where the graph ends, and this doesn't matter if it's an x to the squared, x4, x6, x8, x222 graph. The end behavior acts like a parabola. So we think about parabolas with positive leading coefficients that's like just y equals x squared. What does your parabola look like if it's just an x squared graph? Are you good with that? And I'm going to circle the arrowheads at the end. This means that every single positive even function will have its arrowheads up like that. Let's double check the ones that we did as a starting. I have two. Number 3 and number 4 are both even. See how that has the biggest exponent is even, and that one has the biggest exponent is even. Number 3 has a positive leading coefficient. If I circle where the arrowheads would be, and we should add them on there, the way that the textbook graphs things is whenever it hits the end of the graph, it just cuts it off. you always have to add arrowheads to show that it keeps on going. But if I circle those two arrowheads, do you see how they match up exactly like a parabola's arrowheads, both going up? And if we had a negative leading coefficient, right? If we put a negative in front of a parabola, it opens down. And if I circle the end behavior now, it means that both sides are going down. Did we have any even functions in the one that we did? Yes. Number 4 was even. Notice both of those arrowheads are pointing down at the end. What we don't know is what happens in the middle, right? This x to the 4 graph, oh, got a little crazy there in the middle. Like parabolas are pretty, they're pretty boring. They just like, okay, we're going down, okay, let's go back up. But man, these x to the 4 graphs, they did some crazy bumps and stuff in the middle, so we're gonna have to figure that out. So those are the even ones. This is true for x to the 6, x to the 8, x to the 10. Whatever your leading coefficient is, tells you what the end behavior is going to be. And it's going to act like a parabola. Next are odd functions. So if your biggest exponent is an odd number, a 1, a 3, a 5, a 7, that makes it an odd function, an odd degree function. And for our odd functions, the end behavior acts like lines. So again, we'll look at what happens if we have a positive leading coefficient. Y equals mx plus b. The most simple line would just be y equals x. You know how to graph that? That's a graph with a positive slope. Positive slope goes up from left to right. So here is our end behavior. One side is down, one side is up. And if we have a negative leading coefficient, like y equals a negative x, the negative slope goes down from left to right, and the end behavior looks like that. So already we have developed a number of strategies for matching graphs to equations. To recap, if we look at these first ones, okay, now notice that number 2, right here, graph number 2 is the x cubed graph. It has a positive leading coefficient. That means we need the end behavior to start down there and end up there. If we look at the one that matches up, put the arrowheads on, you see that the arrowhead started in the bottom left and went up to the top right. If you connected those arrowheads with a straight line, you would have a positive slope. But the x to the 5 graph here, notice where our end behavior arrowheads are. The x to the 5 graph has a negative leading coefficient, so it starts up in the top left and ends in the bottom right because it's like a line going down from left to right. Of course, with the x cubed and the x to the 5, there's some crazy stuff that goes on in between. Lines are nice and straight and easy to predict. The x to the 5 graph has some crazy curves and things in the middle, makes it a little bit harder to predict. So, to recap, Your y-intercept is super easy to find. It can often help you with graphing. In this case, all the y-intercepts were 4 when you plug in x equals 0, so that didn't help us very much. We talked about taking a horizontal line, and if a polynomial function goes through a horizontal line, in this case 5 times, it has to be at least an x to the 5 graph. Right? This one goes through 4 times. It has to be an x to the 4. It has to be at least an x to the 4 graph. There are x to the 4 graphs that look like this. And you might look at it and say, that looks like a parabola to me. It's just x to the 4 graphs are like fatter parabolas sometimes. I don't know if that's the right way to describe them or not, but they flatten out more. That could be like an x to the 20 graph. Really flat along the bottom for a long time. So it doesn't mean that if it goes through 4 times that it's for sure an x to the 4 graph, but it has to be at least an x to the 4 graph. Both of these would have to be at least an x squared graph, but they could be much, much higher. Okay? So we looked at that as a strategy, but now with the leading coefficient and the end behavior, that really tells you a lot about the graph. If it's positive and it's odd, if you drew a straight line between your arrowheads, you would have a positive slope. If it was negative and it was odd and you drew a straight line, you'd have a negative slope. If it's even, it's either both going to go up, just like the parabola, when it's positive, or both going down, just like a parabola, when it's negative. So we can use this information to look at each of these graphs. So they've given us a graph. Here's our lines, right? You know that if a line is positive, it goes up from left to right. There's our end behavior. If a line is negative, it goes down from left to right. We have a quadratic equation. If the leading coefficient is positive, it opened up. If the leading coefficient was negative, it opened down. But now as we get to the new ones that we haven't done, our first thought, so I see an x cubed graph like this, I say it's odd. I might even just off to the side draw a line and circle the arrowheads and say, oh yeah, if I have a line with a positive slope, that's where my arrowheads have to be. Notice that this graph has arrowheads bottom left, top right. And here I see an x cubed. I think of a line with a negative slope. I think about my end behavior of a line. And sure enough, this one started top left, ended bottom right. A degree of 4. I see a degree of 4. Now I would think about parabolas. A positive parabola opens up. There's my arrowheads. Sure enough, this one had arrowheads opening up. A negative x to the 4 graph, I think of a parabola opening down. Sure enough, this one had arrowheads opening down. Oh, and that one doesn't even have very many bumps in it. That one's a weird x to the 4 graph. And finally, a quintic, an x to the 5 graph. Again, we're back to odd, so positive, I think of a positive line. Does the end behavior match? Yes. Okay? And with the last one, a negative leading coefficient. I think of a line with a negative slope. And my end behavior ends like that. Okay? And what's going to happen is we are going to graph these. And we're going to use strategies to graph them. So for example, this x to the 5 graph, we might easily figure out that that's my y-intercept. So that's one point that I would know. I would know my arrowheads go here and here because of the end behavior. I might be able to find my x-intercepts. So I would have these points. And I might say, well, what's the best sketch that I could do right now with those points? Well, I'll start at the bottom of my arrowhead, go through this one, go through this one, go through this one. I might draw that. Is it perfect? No. But based on the points that I have and the end behavior, some of it was really good. Right, the beginning part, I was like right on the red line. I didn't have enough points in the middle here to really figure it out exactly, but I got the general shape, and if my general graph could give me an idea of what's happening. If I added some more points, okay, and for those of you taking AP Calculus next year, right, grade 12 pre-calculus is going to give us about this much. We're going to have mostly those points from grade 12 pre-calculus and try to graph the best that we can. Okay? Calculus is going to add these points for us. Now, if you were told to connect the dots now, starting at the arrowhead down here, going through this x-intercept, hitting this maximum, hitting this minimum, hitting that maximum, hitting this minimum, going through that x-intercept. How accurate do you think your graph is going to be? Very accurate. Okay? So what we're getting to is we're developing our techniques to get better and better at graphing. In order to do the AP Calculus next year, or Calculus in university for some of you, we need to have the basic idea of these graphs first to help us with the next stages. So let's look at one last thing, sorry, before we get to example 1 to highlight. Okay, we have something, and this comes up a lot in calculus. We like to talk about local maximum points, and we like to talk about local minimum points. And what's important about and why they're called local maximums and local minimums is because if you drew a circle around each of those points, in that circle, that's a maximum or that's a minimum, right? There is somebody in Winnipeg who is the tallest. We put a circle around Winnipeg. There is a local tallest person in Winnipeg. There is also a local shortest person in Winnipeg. It's probably just a baby, but that's okay. Just baby, they're born. They get shortest person in Winnipeg for a couple of hours, and then another baby is born. You don't want to be the shortest person for like 3 months. Probably means you were born really, really premature, and that wouldn't be good. But we have a local tallest person and a local smallest person, right? In a graph, this one happens to be the absolute maximum of this graph, right? That's the tallest person in the world. There's somewhere. There is someone right now who is the tallest person in the world. And I bet you their life is pretty annoying, because it's not, the world's not designed for them, right? And some baby was probably born just seconds ago that is currently the shortest person in the world. Okay, that's the idea of local maximums and local minimums. So what we're going to do is we are going to see if we could graph things as best as possible. How we could sketch these graphs using the stuff that we have right now. And then we're going to add techniques to this to graph them even better. So for the first one, y equals x cubed minus 3x squared. First of all, I would notice that's an odd function with a positive leading coefficient. I already know the end behavior of this graph. I know it's going to start in the bottom left and end in the top right. So I'll draw my graph, and I'll be like, I know there's going to be an arrowhead here and an arrowhead up there. That much I know already. I don't know what's happening in the middle yet. But if I wanted to know what's happening in the middle, I could find some points. So a very, very primitive yet powerful strategy for graphing is finding points. This is how computers graph. Computers don't do anything super, well, we teach them how to do super high-tech things, but a lot of things that computers do is they can do primitive things fast, right? And if I asked a computer to plot 1,000,000 points on this graph, it'd be like, yeah, no problem. And you would look at it and the graph would be perfect. And it's doing something very primitive, which is just plotting some points. Like easy things to figure out is plugging 0 for x. What do you get for y? 0. So now we have a point. Ooh, maybe it's just a straight line that goes through that. So we plug in another point. Right? You might plug in 1, because it's easy mental math. And you get 1 minus 3, negative 2. So you're like, okay, it's not a straight line. You might plug in negative 1. This will be negative 1 minus 3, negative 4. Okay. We might have to, based on our graph, be like, oh, maybe my arrowhead has to shift over a little bit. I'm not sure. Right? I could plug in, oh, I can write it down. Negative 1 was negative 4. 2 happens to be 8 minus 12, negative 4 as well. Okay. And 3 happens to be 27 minus 27, 0 again. So we could label these points. And be like, okay, based on those points, if I drew a smooth curve through them, this is what it seems like. Is that perfectly accurate? No. How could I get more accurate? Add more points. But at a certain point, you're sort of like, okay, I think I get the idea of the graph. This is enough. Okay? So we could do the same thing for the second one. You could plot a bunch of points. And for the second one, can you see that it is a negative x to the 4 graph? So there's our end behavior. We're not actually going to do part B to save time. All you'd have to do, like, can you see that the y-intercept is 3? Could you plug in 1? Absolutely. Could you plug in 2? Could you plug in 3? It just takes some time, but it's not hard to do. We can always do a table of values and get graphs and get points. So this is the very basic starting point of graphing. And it's powerful because it always works, right? If you're stuck, you can say, well, I'm going to be dumb like a computer and just do lots of points. It's not dumb like a computer because nobody ever says, well, sometimes I call my computer dumb, especially when it's slow. Like, we get mad at computers when they're slow. And they're doing so many things so much faster than we could ever do, except we have expectations that they should be way faster than us. All, like, it should give me exactly what I want when I want it right away. What do you mean you can't tell me the weather in Dubai right now? How long would it take you without a computer or any technology to find out the weather in Dubai?
However long it takes to get there.
However long it takes to get there.
Area pigeon.
Be very. Anybody know what's happening in Dubai right now?
It's like flooded or something.
It's raining.
Because they seed the rain seed or whatever.
Oh yeah, rain seeding. That's the controversy. But they had more rain in one day than they normally get in a year and a half. So to make that equivalent, it would be like if in one day it rained about 75 centimeters in Winnipeg in one day. That's crazy.
Do you think they want the rain though?
Yes and no, right? They want rain,
But now it's flooded, not
but
bad.
now nobody wants too much of something, right? When it was cold in winter, you wanted it to be warm, but if it turned out to be 70 degrees the next day, we would complain. It would be a problem. Okay, so questions for this one? 5, 6, and 8. But the good thing is computers don't have feelings yet, so you can get mad at them and they don't mind.